We're going to continue with a little bit more review of relevant digital logic concepts for this class. Somebody took the... Yeah, here we go. Multiplexers. We had a question on the quiz about basic multiplexers, but basically it is a data selector. If you have 4 input lines, you need 2 select lines. B and A. And the select lines, you get your inverse of the select line and the inverse of the select lines. And see here. Let's see here. A would be with S0 and S1 being low. So let me adjust this a little bit. Out here. So you would have A ANDed with the inverse of each input. So it would be 0, 0 would allow A to go through. Uh, 0, 1 would allow B to go through. So you would have 0 and 1. One and 0 for 1 and 0 for C. So see here, and then D would be 1 and 1. So you would have one of these would be high when the input is high and low otherwise. These to be brought together would be with an OR gate. A 4-input OR gate. So you have your data selector right here. And then the results ORed together afterwards. This is when you have multiple options of what data you want to pass through, you use a multiplexer such as this. Okay, the demultiplexer, let's see here. Well, a demultiplexer is basically a subset of the previous diagram. So you have two lines, S0 and S1. Take inverses of each one. And then you would have AND gates. So if both inputs are low, your 1 would be out. Your output 1, or Q1, would be high. 0, 1 would be let's see here, 0, 1 would be Q2. 1, 1, 0 would be let's see here. Q3. And then finally 1, 1 would be Q4. So you can select which output is going to be high depending on the binary number of the input. One thing that you'll commonly see in data sheets is the use of the letter Q for an output. That's because O for output is easily mistaken for the number 0, which is, one of the binary digits. So Q is used instead. Just a little tip for reading data sheets. Let's see here. Quickly go over adders. You have the half adder. Then you have, let's see, the full adder, which is I don't know if I'll have enough room for this, but I'll give it a shot. Let's see here. The carry, yeah. Carry. And then I don't have enough room. That's the sum. And then let me get rid of this. The output for the carry is A and B added, ANDed together, and the carry and first sum ANDed together, and then these two ORed together. And this is the carry in. So, and that's the full adder. Get rid of this. That's the full adder. And the state table for that I'm gonna run out of room here. And that's your carry out and sum is going to be 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0. Come on. Let's see here. How can I adjust this? There we go. It's 1, 0, and 1, 1. Zeros here. So with these, you can add 3 bits together and carry out the next bit to the next adder. For the for a multiple bit adder, doing adding two 2-bit numbers or 2 3-bit or 4-bit, whatever numbers, you would string these together to create a ripple adder, where the result ripples from one end to the other, from the least significant bit to the most significant bit. Some folks are still writing, so I'm going to wait to clear the screen before I show you how ripple adder works and how it is used in to make a subtractor. Let's see here. All right. Let's see here. Yeah, you take a full adder, which you can represent with as a box with the FA in it. And you have your A and B inputs. So you would have A0, B0, A1, B1, A2, B2, and B3, A3. And we'll get to the subtractor in just a minute. But your S0 carry out to carry C in, C out. And yeah, and this is a ripple adder. It ripples down the result is valid here, and then it becomes valid here, then becomes valid here, then becomes valid here, and here. So the result is not valid immediately. There are what's called look-ahead adders that are much more complex, that the result is valid at the same time. But for simplicity's sake, this will work for most arithmetic logic units. If the logic is fast enough, you wouldn't notice the difference. So now with the, to make this a subtractor, yeah. Full adder with with no connection on the carry in. But in practice, it is, and I'm going to get to that in just a moment. It is connected to something to make it a subtractor. To subtract, you make the second number negative and add it to the first number, right? You do that by doing 2's complement, which is inverting the second number and add 1. So what you do is, let me right in here. Oops. On your input that you're going to subtract, you have an exclusive OR gate That's not a connection there. That's there. And then you would connect that to your carry in, and that's subtraction. If the subtract line is high, then A is inverted, and you add 1 through the carry in of the first full adder to make it a 2's complement, negative number. So that makes a ripple adder subtractor. Because if you recall, exclusive OR can be used as a selective inverter. You raise one line and it selectively will invert to the other line on the output. So the use of a exclusive OR on the input, and this will basically make B plus A or B minus A. So two math functions using the same, essentially the same logic. So let's see here. Review of latches. Let's see here. April's still writing down, I see. And we'll just cover latches real quick. Primarily the D latch. Let's see here. And let's see here. Oops. And that's Q bar and Q. And this is enable. All right, so this is a D latch. Basically, the Q follows D whenever the enable is high. When the enable goes low, it latches on to the last value of D and holds it there, essentially making this memory, a single bit of memory. It will store the value of D as long as the chips have power, much like RAM. I believe static RAM uses this type of configuration or something similar. Dynamic RAM, the big RAM in your computers, laptops, and that sort of stuff, use a very different different technology. Won't get into that too terribly deep in this section here, and you can make this a flip-flop where there are two types of flip-flops: the positive edge and negative edge. The positive edge will take a snapshot of D and pass it to Q at the rising edge of the clock. The schematic for that is a little bit complicated. I don't know if I'd be able to put it on this board very clearly, so I won't even bother. You won't be tested on it or anything like that. But it only takes a snapshot of D at the positive rising edge of the clock input. Likewise, the negative edge triggered flip-flop is when it'll take a snapshot of D at the falling edge of the clock input. So when the clock goes from high to low, it'll take a snapshot of that instant to pass that D to Q, and the inverse to D bar or Q bar. Those basically form the basis for memory cells and registers. You can link these together by doing so you have, in this configuration, edge triggered, positive edge triggered D flip-flops. That's what the clock here with the symbol here means. That is a positive D flip-flop. and you have D coming in and your clock in. What happens is, in this situation, this is what's called a shift register, where at each clock cycle, the data on D gets moved one space. So if you have 1, 0 coming in, if you have 1, 0 coming in, and 0 goes first, so you'd have 0 clock cycle, like this. The first clock cycle, 0 would be transferred to here, and that would be your B0, bit 0. Your next clock cycle, 0 would be transferred to here, and 1 would be transferred to there. And here you would have B bit 1, and here you would have bit 2. And the next clock cycle, everything would shift again one position. That's how you would translate a stream of 1s and 0s into a parallel. So this is a serial to parallel shift register. Each clock cycle would, in turn, shift all the bits to the right one position for each clock cycle. And the data coming in this case, was 0, 1, 0, 1, and then 0, for example, there. But the serial to parallel shift register. Did Manzul cover this in Digital Logic? No, he didn't. Oh, okay, okay. I can't remember if I did in mine or not. Oh, I didn't. Okay. Well, that's right. We did cover the latches and the flip-flops, but this is how they're linked together with to make a serial to parallel shift register. Something similar to this is a frequency divider, where you have your E, Q, Q bar, clock, where you have your clock here, and you have this is a frequency divider. Am I running long on time? Oh, okay, we got a little bit of time. The frequency here of the clock is going to be frequency divided by 2. And the frequency here is frequency divided by 4. Because at the first clock cycle, Q is going to be 0. Q prime is going to be 0, making D 0. And then the next clock cycle, because D is 0, Q prime will be 1, and that will be a 1. The next clock cycle, and so on and so forth, it divides the, so if your clock is this square wave here, your frequency that's F, and that's F over 2. Your frequency is going to be half that of the original frequency. And, you know, F over 4 is going to be like so. Yeah. So your peak to peak each step in the frequency divider divides the frequency by 2. So if you were to add another block, this would be frequency divided by 8. Well, I mean, yeah, there you go. Frequency dividers are often used to interface with slower behaving peripherals in processors. So this is how they generally will work, using these D flip-flops. Or when used in this configuration, they're sometimes called T flip-flops because they toggle. And so the T flip-flop is a D flip-flop in a particular configuration of its inputs and outputs. So I think I kept you long enough for that. Got 4 minutes left, so we'll call it a day there, and we will get into memory concepts starting on Friday. Have a good day.